of a high dimensional system if you have scales. And I had two approximations. One is a classical approximation, which we call advective scale, where the average system is a deterministic vector field. And the difference between the averaged and the original converges, or normalized difference converges to a Markov process. The second one is when you have a centering condition, then you have the average system is a Markov diffusive process. And then I went and did some problems where there are homoclonic orbits where you can't do traditional averaging. We call them non-standard averaging procedures, where you have to glue the trajectories along the homoclonic orbits. So roughly what we did was how to use scales, especially time scales, in stochastic differential equations to bring them to a lower dimension. So one of the examples I was using for the advective time scale is a system like this, in which I have Z, which is a very fast process, and then you have X is a slow process. They are coupled together. We went through this analysis and showed that you can actually bring the average process to this equation. And then I plotted here the average process and the initial process. They approximate each other for a sufficiently long time. And then we did different things. We don't want to go through these things. So, where? I'm sorry. Twenty-four, I'm sorry.
Yeah.
Huh.
Okay. So, the evolution of ZX did not have a stochastic component to it.
Correct.
So, that makes, jointly, individually none of these processes are Markov, jointly they are Markov, but it is non-degenerate, it is a degenerate stochastic ISG.
Yeah, so this is basically, there's no, the average process is a deterministic process.
Yeah, that is okay. So, but you face any difficulty in average process, I understand that you are okay with. But if you are looking at the absolute point independent limit, then the degeneracy of the noise, that's not a important problem.
Not here.
Not here, actually not because
Oh.
the recent process it is non-degenerate. So there, that is where you need the effort.
But individually that process is not Markov. So,
We have to use the fact that the Z process has to be ergodic to some extent. So that is important. The Z process has to be ergodic.
I understand that, but if you put the ergodicity in all those equations and not nice Markov in structure, then you can work on it. But individually, just when you look at Z itself, that's not Markov.
Z, but
X jointly are Markov, but Z itself is not Markov.
no, for a fixed X.
Fixed X, of course.
Yeah.
Conditional ergodicity is what it is.
The reason actually I'm looking at different time scales, right? If I look at the time scale 1 over epsilon, I go to that particular time scale. In that time scale is what I have this. Beyond the time scale, I can't say anything about it. So these are the averaging results you have, right? It is, we take the time scale, and on that time scale is what this result is. So, we come back to this. So, this is what we have. This is roughly what we talked about. So, technically, you have a system in 2 time scales. I have an average process which looks like this. So, lecture 2, I would like to add observation to this, right? The observation I have is Y, and all of us have gone through this observation from Dan to Roman, and also Rajiva has talked about filtering. So what we want to do actually is whether we can use the fact I have a scale in my dynamics, and if I want to understand the slope process, I want to find the filter for the slope process, does it have a lower dimensional description? And it looks obvious. We want to go and show it does. So we will now, from now onwards, I will assume the noise to be white. So otherwise we'll have to have more algebra. So I have two stochastic differential equation, and my observation is given by y. So this is the same slide as the last slide, except I've assumed the noise to be white or Brownian motion. So we will just a review of filtering. So what we have, I have a test function phi of the slow and signal. Signal is both slow and fast. Given the observation, that is a measure valued process here, right? So, and my Q is the original probability space, probability given in my original space. And then the standard technique is to define a Grusnov, that is respect to the sensor function. Okay? So distributions of x and z are the same under P epsilon. This is a standard stochastic analysis result. So what you have to know is I want to find, this is what I want to find, and this is given in terms of an unnormalized density U, right? So if I want to find the expected value of a function, I need a conditional probability, and the conditional probability can be given in terms of unnormalized density, and you normalize with respect to U multiplied by phi. Phi is your test function, right? And this U has a nice partial differential equation, and that's what we want to play with, because that is linear, and that's called Zaka equation. So this is the inverse of that, right? And of course, y, this is the conditional expectation with respect to the conditional probability. If you have a conditional law has a density with respect to a back measure, U is your unnormalized density, and this is a normalizing constant.
What's that symbol one with a...
Normalized is I...
No, that one, yeah, that thing.
Indicator function.
Of what?
Oh, something is missing here. Basically, it should be f is equal to 1, is the phi without phi. So just the normalizing condition here, right?
So we could just remove that, right?
Remove that up.
Yeah,
Yeah.
okay.
So, thank you. Something is missing, yeah. So you come to here, look at this one. This is fine.
Yeah.
This is exactly what we should look at. So now U is your unnormalized density, and that is given by Zaka equation. So Zaka equation is a partial differential equation driven by the observation y. And this is, so if you look at this structure, this is the Fokker-Planck, right? If I have no observation, this is what you can do. Given initial uncertainty, that will evolve as a Fokker-Planck equation. And whenever you have observation y, that modifies. So it is a data-driven system. This is a partial differential equation driven by my observation. Okay? And so now this L, epsilon, has two components. One is a fast component, which is to some extent the atmosphere for me, and S is my ocean. My problem has physical meaning. I have a fast generator that comes from my atmosphere, and the slow generator comes from the ocean. And these are the two generators, and this is what the starting point of my problem is. Of course, U0 is the initial unconditional density, unnormalized conditional density is the same as the initial density. This is what Dan and Ramon has been talking about. So this is the starting point. Okay. So instead of looking at that U, I can also look at, if I take the inner product of U with respect to a test function, you will land up with a measure valued process. Either I talk about this equation or this equation. This is the unnormalized density. This is the expected value of the test function of x and z. One is a measure valued process, other one is a density function. So these are the two equations I will go in between. So at this stage, okay, if I want to solve this, I apply particle methods, solve them, but because the dimensions are very high, they will become degenerate. So now I want to ask a question, because of the fact I have this slow, fast stuff inside, is it possible to reduce the system? And so I give you, everybody has given a picture about how things work. So this is my picture. So since I have it, I'll give it to you anyway. So you have an unnormalized filter, and so this is a real true trajectory of a point which goes here, and of course this is the uncertainty of my initial point. So if you leave this, the Fokker-Planck equation will just take you all the way here. It gives you a new density. The mean value is given by that, all right? So now, of course, what the Zaka equation does is to give you the observation y is given by green, and that modifies my blue and makes it a little better. And it does it continuously, right? So it is a data-driven system where the system is evolution is your conditional law. Okay, yeah. So now comes the particle filters. So I think I've talked to many people. This crowd doesn't need any doesn't have to be convinced that particle methods is the way to go. Right? So if you want to solve these problems, we need to have a lower dimension, because at higher dimension particle methods really don't work effectively. So the question we had was, we want to reduce the dimension because of the curse of dimensionality with respect to signal, not about observation, right? So our interest is to estimate the slow process xt given the observation y. So I want to now estimate this. So I want to find a lower dimensional filter which calculates this conditional law or the density associated with this conditional law. And I'm hoping that that law is going to be given by a lower dimensional generator. And that lower dimensional generator is exactly same as what we derived in the last lecture. That is the reduced dimensional system, right? And that is roughly what this talk is going to be. So you have again the same picture, and you want to find the conditional law of pi, or the coarse grain dynamics converges to something of this kind, and this is what the new averaged filter is going to be, and is going to be given by a stochastic partial differential equation. It's not a Zaka equation. It's going to be a stochastic partial differential equation as opposed to being a Zaka equation. Okay, clear?
In this case, when you say converges
As
as what goes to what?
epsilon goes to 0. The time scale between the fast and slow. Yeah, for each time. This is a time. This is a filter. It is a for every time, every t, it has. Okay. So I think as in the first talk, I think Rajiva has actually showed an example where just because x epsilon goes to x0 and y epsilon goes to y0 doesn't imply the filter pi epsilon goes to pi 0. Okay. In this case, he had an example where there was no dimensional reduction, just xn going to x0, right? There the condition was random Dechem derivatives also have to somehow converge, right? So here you will see it is not just because x epsilon goes to x0, y epsilon go to y0 doesn't imply the filter goes to 0. You need some little bit more tedious calculation. So I'm going to start with a very simple example it gives you a sufficient illustration as to what goes on. I mean, I can't find a better example or simpler example than this. So I have a very fast diffusive angle. I have a Brownian motion just going theta. So theta is a very fast Brownian motion, right? So it's called a quickly diffusing angle. X you can think in terms of action if you're a Hamiltonian person, or just a one-dimensional variable, which is actually driven by, of course, Brownian motion, which is independent of B, but also this theta process. Right? It's a coupled, fast, slow system. This is the simplest example you can think in 2 dimensions. You can go through it a little bit more carefully, then you can see the big picture. And also, I'm going to show you how we thought about this problem, right? So intuitively. So, as I was telling Professor Mitter, I'm an engineer. I think in terms of as an engineer. Then we figure out how to got the answer. Then we go and make sure things are a little bit more rigorous. So intuition comes because I come from the applied side. So look at this particular problem, and then you have observation y, and y actually is a function of both theta and x. So, and we also assume, because I want to use averaging, there's some periodicity in theta, right? And B, W, V are all independent standard Brownian motions. So, what I want to do, I want to understand xt, probability of xt belongs to dx. So dx, I'm using as opposed to a, dx given, scandalous, but having density. So in terms of, so this is what I want to show. So where what I mean by this is all the information up to time t. We want to understand the slow part of the plant conditioned to observation. Okay, this is the problem. So what would you do? So I will say, hey, I have these 2 scales. So if you are a physicist or an engineer, you average things. You said, oh, just remove that theta out. So you want to average this theta, and you will land up with something completely in just x, an effective x bar, like what we did the last time, right? And you see here, of course, you shouldn't average it, but what you will do actually is, you look at this, hey, this theta is very fast, right? I can average that also. It's absolutely fine. I will have an effective h bar. So this is my problem. This is my thing, this is my red. I think I have too many pictures. Sometimes I do it in my grad. So what I will have actually, when you take the time limit of these 2, of course, dx0 is my effective plant. My plant doesn't have any more theta. I have a b, and the b bar is average value of, I'm taking the period to be 1, so it is average value of this. What do you get is b squared. It's a diffusion. So square root of b, you're going to get a square root, you get a b. And that is my axial effective process. And this is my effective observation, right? So now you ask yourself, what is the filter for this? I have an observation, I have a x. So the filter for this is somehow this one, okay? Given xt epsilon belongs to dx. So you want to ask yourself, does this one somehow becomes this one? This is the question you want to ask. Is it clear? It's just this is the way we're thinking. We're thinking about 4 years, 10 years ago, 6, 7 years ago. This is the way we're thinking, and this is the way we sort of start looking at this problem. So with this is my effective averaged system, signal, and average observation, right? So come back. So how do I get x? So what I want actually is, remember, what I want is this. See, this has to converge to this, not x and theta. This has to converge to that. So the question actually is, so how do I get this? So if, of course, we know I can solve for u of x and theta. The original Zaka equation solves theta and x together. It's not decoupled. But if I integrate my theta out, I get a marginal. Our density, I remove one variable, I get a marginal. That marginal is this part here, and then I integrate that respect to x over set A, and that gives you this. Correct? So this is what I want. Therefore, I have figured out how to get this part. Now I want to show this part somehow converges to this part. This part is going to come from here. Roughly, details, you have to go and look at the papers, but just to get this. But then you ask yourself. Yeah.
Sorry, I was a bit confused. Can you go back? X naught is not xt epsilon with epsilon equals
X naught is a limit.
At that time I was, but no, x naught is the right hand side.
I'm sorry.
The right hand side of the last equation.
Yeah.
Is basically the filter for the
Y0.
Yeah. But that's, so if I just put on the left hand side epsilon equal to 0, I will get the same symbol, same looking symbol. It's not the same thing.
Yeah, this is my Y0. That is my X0.
Yeah.
So I say, okay.
But that is not the same thing as the previous system with epsilon equal to 0.
No.
No, that's why I said.
So
I'm a bit confused.
yeah.
With,
So I'm just saying, okay, you go and filter it, you go average it, you get this one. You ask yourself, what is the filter for this? You can write it down the filter, right? That's exactly.
Just notation.
Yeah.
Epsilon can take any value. In particular, if you take 0, you would get right.
No, the limit is what we are talking about. Limit here is what we are talking about. Okay. So you have, so the question is, now I have u. U is given by the Zarka equation. Zarka equation is what we talked about here. But the problem actually is, see, the Zarka equation, we bring it in terms of Brownian motion, and this is a nasty term here. Okay, this is a nasty term here. This is a stochastic process xt and theta t, right? And this is a Brownian motion. And this is what we want to understand: how to get the limit of this as epsilon goes to 0. It contains some work. So the real part of the analysis is to look at some sort of Feynman-Clark formula. These are the things where you have a process like this, which is very fast, and this is going in the wrong opposite direction, right? So backward and forward processes will come. This is sort of where the real analysis relies on. But for the sake of just to give a picture of what's going on, you ask yourself, u epsilon can be expanded in terms of u0, you are physicists, plus a correction term. This is what you do in homogenization. A correction term and a remainder term. So what we can show is u0 is exactly the Zarka equation which I just mentioned to you before for the average plant and average observation. U0 satisfies this, and one can show phi 0 and R0. This is where you need this Feynman-Clark formula, which is large amount of estimation, goes to 0 as epsilon goes to 0. Therefore, u epsilon converges to u0, and roughly this goes to this. Right? This is a rough statement. So then you ask yourself, what is y0? I've got a very simple problem. This is the simplest example, where I have diffusions as the Brownian motions, as my angle, and I have Ix is just a simple one-dimensional process. One can show u epsilon goes to u0. But the sad part actually is, observations that I have are y epsilon. What I have used in that simple example and also in the proof is somehow something driven by y0. And y0 is fictitious. Y0 is, I'm just removing observation I have taken. Why should I waste those observations? So we call this, this grant came to us during Iraq War. So we call it, so we paraphrase Rumsfeld. It says you filter with the observations you have, not with observations you might want or wish to have. I don't want to repeat what he said, but this is, for those who are from the States, it makes sense. But for those who are here, may not be. But this is anyway, this is an Air Force funded grant. And therefore, I was so gutsy enough to go and say it. And one of the guys, he was completely perturbed by the way I said. I call it Rumsfeld's dilemma. Yeah.
What if, I mean, you're saying that y epsilon has all the values, the theta. But what if, I mean, this, you're talking about real physical time scale based on the moment. What if this time, the fast time scale is too fast for the instruments, or for the way you make the observations? So is there a really, what you're observing is really a function of theta, or say that the theta evolves too fast for the instrument?
Yeah, theta actually, what we are saying actually is this. I have a process that is theta, which is very fast, and that is influencing the slow process. But the observations are recording both theta.
But do you know that the observations that you're recording is really theta? If say the time scale of theta, if it is too fast for the instrument, let's say, could you say that you're actually measuring theta or an average of theta?
What we are saying, yeah. So that is a second that we haven't. Yeah, there's a second kind of thing. What is instrumental? What is possible? But we are assuming here that theta is theta. This sensor is an instrument. All right. It basically measures many things altogether, which are different time scales, and therefore you have no real choice to say the sensor is only measuring the X process. So I'm assuming sensor does everything, right? Yeah. So I don't know about the instrumentation and all these things. No, this is a second question. So this is where the problem comes. So I said to come out of the conundrum, this is exactly what Rahul and I was discussing before. The filter is a map from observation to conditional laws. So I want to ask the question, because of this fact, whether we can, so what we have is, this is what I want, this is what I got. What I want to do is, I want to replace y0 in this one by y epsilon and show this is close to that. So now I have phi 0 with the real observation close to phi t. This is the one I wanted, and this is the what I have now, and they are basically. So the next step actually is to show. It takes a lot of work, but what we have shown is to show I have a lower dimensional LS. L was S and F. LS of V and driven by y epsilon. This is my new filter. It is not a Zaka equation, but it's a stochastic partial differential equation. And this is roughly what you have. So the real answer, real theorem actually was in 2009, 2010. We basically, it's in 2 dimension. Basically, this is the original marginal of my filter, and this is the homogenized filter. They approach 0. So now I'll do a simple problem. So I won't do a simple problem. I go to higher dimension. So that was very, very easy because things were nice, right? Now comes the hard work of really looking at high dimensional systems. In high dimensional system, I can't use some of the techniques I used here because I could just shift. I use Levy shift of time by which I could do so many things because it was 1 dimension. But here I have m dimensions and n dimensions. So we have this is a general system I want to look at. Now this is really the ocean, all right? And this is about 5,000, this is about other 10,000. I'm only interested in the ocean. This is my observation. How do I find a lower dimensional description? The same, this is the last example gave us idea as to what to expect. So of course here L is not equal, because before last time was diffusion, very simple. L is equal to L star, things will go through. So, but here we have to do, in fact Dan has left, but I was about to tell Dan about his book. There was a nice, 3 or 4 nice sections which we have used here. to get a particular thing called backward stochastic differential equations. So let me come back here. So this is what I have. This is my measure valued process as I've defined before. It is equal to phi is a test function. This is my unconditional density Zx. X marginal is what I want, is basically I integrate my Z out. And this is exactly same as phi with the probability measure here from 0 to t. So from the last two-dimensional example, I can see what do I expect to see as a homogenized filter is a measure valued process driven by L bar, which is my homogenized generator, driven by actual observation. This is what I want to get, right? See, this is from the last example in 2 dimension, we got the idea this is the right kind of instrument to get, right? And we're going to now force our answers to show this is exactly what we'll get. See, this is, okay, as I said, I'm not a mathematician. I can't figure out what to get, but by intuition, we got some nice results, and then in higher dimension, we are assuming same thing is going to work, and it worked. So you have now L bar is now this averaged homogenized generator, which is the one we talked about in the last lecture. How to find L bar. L bar is obtained by homogenization respect to the invariant measure respect to Z. This is your fast dynamics. This is my diffusion process. Again, this is my invariant measure of the fast dynamics. And this is the new filter I want to get. And, okay. So the answer here is this. The same answer as before. I can show in the LP, the pi epsilon x is close to pi 0 in LP cells. Okay, this is the result we want to get. So to get to this, I won't go through the details, but I'll give you some small thing. This is what the key is. So this is what I want. This is what I defined as a measure valued process of phi is a test function. That is your conditional law. And if I use a Markov property, okay, the Markov property will allow me to go, instead of going from 0 to t is my terminal time. Okay? So 0 to t, because if I use a Markov property, can be given in terms of t to capital T and 0 to t. And this t to capital T is a dynamic version of this quantity. And so I would like to ask the question, what is the equation that governs this dynamic part of this equation? And that is where we have used some of the results in Dan's book. And this is the dynamic version. So T, this is the dynamic version, which is given by, I define this as a V, which is going to be the solution of a partial differential equation. And this is what my average ones are. So I want to basically show Vt goes to this. But the equation that governs Vt is given by, this is from many places, but Dan's book is a nice source, is given by this equation. This equation is driven by a noise going backwards. It's a partial differential, stochastic partial differential equation driven by a backward noise. The reason we have to go this path is to use a set of results that are available in backward stochastic differential equation, which allows us to see this is a partial differential equation, and it's quite difficult to find estimates for stochastic partial differential equation. But if you have a finite dimensional system, by going to results in backward stochastic differential equation, which are finite, I can use those results in estimating these answers. And that is a
Just a point of terminology.
Yeah.
What people call a backward stochastic differential equation is not this, right?
This is the backward. This is actually backward stochastic partial differential equation.
If you read BSE, the backward stochastic differential
That's different.
equation is completely different object because it's adapted to the forward filtration. And this one
Yeah.
is adapted to the filtration of
Backward.
But
But
it's a reverse time ordinary differential stochastic differential equation. It's not a backward stochastic.
this is a backward stochastic partial differential. But why is that? Y actually is going backwards.
Right.
Yeah, but
So what people
yeah,
call a backward
yeah.
stochastic differential equation has a noise going forward,
What-
and it has a terminal.
I'll cover the next one. Next one is where it's going to be. Okay. The solutions of this will be given in terms of stochastic differential equation which are backwards.
Right, which is not a backwards.
Not backwards, correct. Okay.
This is very confusing terminology in the literature, so I
Yeah.
just wanted to
Okay.
clear it up. This is a time reversed stochastic.
Okay. So the question actually is, now we want to go and solve for V0, psi r, exactly the same way we have done before. And then, I don't want to go through the boring part of this. So what we have actually is, so we basically can show this is my lower dimensional filter. So the whole part of, when I see equation is of lower dimensional partial differential equation, driven by, all right? This
My point was that it's the dimension of the observation that matters for the first dimensionality. But it doesn't mean that if you can reduce the dimension of the state space, that wouldn't make a huge amount of difference.
It makes a difference.
I mean, it's
Yeah.
just a difference.
Yeah.
So this is not a this is the first dimensionality.
I'm not asking about, I'm not addressing this question at all. That is important.
It's still an important thing
But
to do.
maybe next year I'll talk about it. But I mean, I'm talking about just assuming I have finite dimensional observation, all right? Even the calculation of a particle filter becomes much easier. You can actually see it with examples. So, okay, now we talked about particle filters.
That is what surprises. So you said that you mean the calculation becomes easier.
Computational time.
Computationally,
Computational time.
scaling.
No. Computational time is really reduced.
It becomes easier for the same reason that it can reduce the dimension, even simulating this.
Yeah, it is exactly. So if I want interested in the ocean, I can use this.
And you have cut out the atmosphere, then of course.
But I won't cut out completely. No, don't say cut out.
Cut out in the sense
I've used it inside, exactly.
you don't have to actually do
Solve it.
something on the atmosphere.
Yeah. So I've intelligently used it.
Cut out in the sense?
Yeah.
Just to make it precise, the claim is that if you have finite dimensional observations, the particle filtering is just as hard as simulating the underlying system.
Correct.
But if you have high dimensional observations, then particle filtering is exponentially harder than simulating the underlying system. But, you know, if you can cut the amount of time it takes to simulate the underlying system by 10, that's also, even with high dimensional observations, it's also going to cut the amount of time it takes to run the particle filter by 10. I mean, you know, so it doesn't mean that's,
Absolutely.
you need to
Yeah.
go.
So what we want to, so we'll start with just to ask how do I solve this? I want to use it with particle method. So we will start with what yesterday you gave a talk on it, and also today Dan gave a talk. And so you have n particles, all right, the same way as Dan has talked about. And x is a position and w is your weights, right?
Actually, so one more question. So in the final filter, the only place epsilon enters
Is
is
an
the observation.
observation. So observation is the real observation, all right? So I take the observation, I don't do anything to the observation, I want to use all the observation I have taken, and then I do use that observation to drive my system. So if I have used y0, I'll be wasting my observation, all right? Just, so that's sort of, so I have now, I'm looking at continuous time, even though these calculations are. So I have a Zaka equation. Now, okay, so even though it's on Zaka equation, I call it Zaka equation, it's a SPDE. So for Kaplan part, and this is my H bar is your homogenized, L bar is your homogenized. So you basically put a bunch of particles and you go forward in time, particles will go here, and they have moved to different parts. So what happens is when you collect the observation, so this here is your Kalyan-Possible formula here. This is your weight. The weights will change according to this particular formula. So now instead of using H, I'll use H bar, which is my averaged H. And here is my H bar again. This is the calculation we have to do to change the weights. So I change the weights, I have a posterior, and then I keep going. It is just a very simple particle filters where I use average generator and average sensor functions. So I take a very simple example that I've used before. That is my one dimension. Okay, now I'm looking at the observation. Observation is this. So this is, of course, now I put observation is green, I believe, No, I'm sorry. Yeah. So observation, so the green is my fast process, red is my slow process, observation is blue, all right? And this is my average process. This is my average process as I have explained to you in the last lecture. It very nicely approximates the average process. Now comes the filtering part. So this is a two-dimensional system.
So the observation in this case does not depend on Z.
No, X depends on Z.
Yeah.
Yeah.
So the question that we had was, if your H also depends on both
Yeah, but
Z and X explicitly.
that's the way I have done the theory. My Y depends on X and Z, all
So
right?
in this case, H bar will be equal to H. Is that right?
Not really, no. Because, because the one I have is dy. In my formulation, I have dy. So dy is going to be equal, if we take the dx on the right hand side, the whole dx will come from there. So it becomes a mess.
What do you call it? H, the observation function?
Yeah. Yeah, because
What do you call it? The sensor function?
sensor function.
Is that the same? H and H bar?
See, in my formulation, I have dy, all right, is equal to this dt plus dbt. And this was a function of x and z. Yeah.
And then
What is
the
the example?
average.
So in this example, H and H bar are the same.
H and H bar will be the same, roughly. Yeah, sorry. Okay. yeah, I'm sorry.
That's what I said. H and H bar in this case.
In this exactly. Yeah. Sure. I'm sorry. I thought this is what we had there. Okay. Yeah, this example. So now I take this example here. In this example, I have a full particle filter, which means I don't do any reduction. I apply the particle filter, of course it follows very well. It took about 447 seconds. And this is the homogenized one. It takes 17. So this is the whole point actually is you can get the same answer much faster.
Did you move from 2 dimensions to 1 dimension here? I mean,
Yeah.
how much?
Two
So
dimension,
what
1
accounts for the fact that you didn't just cut down the time in half?
I count by much more than half.
But you've just halved the number of dimensions.
Yeah,
So what makes it so much faster?
because the amount of simulation that is needed for this process.
Why is that such a complicated process? I guess I don't understand.
The full process because you have the fast time scale. You have to do it.
Oh,
Yeah, fast.
It's a stiff system.
That's the fast time scale, right?
I see.
Yeah. That is a Z. Z is the one that gives the time.
I understand. You can't run them on the same.
No.
Yeah, I understand.
Yeah, that's the reason why.
Okay, thanks.
The Z is a problem for that.
So you ran that, the first one, on a much finer.
Of course, I had to do it because of Z. Correct. So to resolve the Z, so there I can effectively, the whole point is 17 seconds, right? So but you can also see, in fact, when I gave the talk, it looks more accurate, all right, than that one. Yeah, I thought somebody will ask the question. You know why? Because the number of particles was exactly the same. I used 500 particles. It's too much I put too much particles for a one-dimensional system. It was so accurate. So I could have lived with even 100 particles to get the same approximation. It would have been much faster. So it is really, so we just blindly use the same number of particles. But this here we have used more particles than needed, roughly. So this is a very simple problem. So now I take a second example where I have a diffusive limit. So this is a little more complicated because in this example, my average process is a deterministic process. But here, my average process is going to be a diffusive process because my centering condition works. Therefore, I have, this is my, my fast scales. This is my slow scales. I have 1 over epsilon squared, 1 over epsilon. Too many scales here, but this is a much more tedious problem. So my H is given by this. H is a function of all variables here. Right? So if you do homogenization, you will land up with a B bar and a sigma squared, and they are given by this formula here. They are done computationally, right? They are not done by analytical. Computationally, where mu x is obtained from these set of equations, right? This is my fast process. To find the invariant measure to average this, I had to use this process. So, and here, here again we used the full particle methods, and this is where homogenized particle methods. In fact, we didn't put the time scale here. Wow, it is almost half. Believe me, it is. Then you can almost the black one is the true signal. Red shade spread or estimate one variance. Green is about two variance. Spread. It's a diffusive process, right? Spread. So I think this sort of gives us. So now comes chaotic system. This is my talk for tomorrow. I must have finished pretty fast. Ooh. So the chaotic system. So the question we have is, now I would like to ask a question: how do I do this in a chaotic example? So far, system is pretty nice. There's no chaos. So things were nice. Now the question actually is, you have a system in which you have positive left-no exponent, and what happens if you do the same methods I have showed you now? You will see, if you are continuously taking the observation, you can manage it, which means continuous means every time step I'm having an observation. But in reality, you don't have that picture. You assimilate data every 12 hours. So within that time, because of the fact things are chaotic, any small mistake you have in your initial conditions or your estimation will really diverge these particles. And for that, we will use nudging. And that is the stuff that I won't talk about it too much. I'll just explain to you. The whole point actually is you need to control these particles. Knowing the observation, control. So we apply control theory to particles, and the particles. So what kind of control you put to the particles is, say, when you do control theory of a plant, you have a control actuator. You have to figure out how to put those controls. Here is an artificial thing. Therefore, I have a little bit more flexibility to use the control. At the same time, I don't want to put too much control, because then you lose the diversity. So it's a very subtle thing. So we want to use sort of a control theoretic way to apply, steer the particles towards the observation, so that the posterior, the prior will improve. And that's exactly what we're going to do tomorrow. So next lecture, we will just basically talk about optimal nudging of particle filters and apply them to chaotic systems. So I think we're all tired. I will stop here. You can ask me questions. So thank you. I must have gone pretty fast. I don't know why. Yeah.
I had a question. It is enough to work with Zakkai equation. You don't have to work with the normalized equational equation.
I think we didn't have too much problem working with the Zakkai equation. But please tell me whether maybe there is. You are a master of filtering, so you may know things that I don't know. So you can tell me what would be the problem just dealing.
There are situations where the normalization I don't know. Just.
We have used Zakkai equation as running examples throughout the thing. So maybe we haven't seen any nasty things so far. Yeah. Okay. I can talk to you later about it. Yeah. Any questions? Yeah.
No, my question is, I think it's rather from what you will talk tomorrow. I'm pretty sure.
On this one? Yeah. This is actually, yeah.
I'm really curious about all these plots again. So this is in the space of observation. So on the y-axis are the observation, right?
No. I am looking at the. So I'm saying no. So what I'm saying actually is tk and tk plus m are defined because I get a observation here and observation here. From here to here, there's no observation. The observations are discrete. And through this thing, we want to nudge the particles. So so what we are doing is, think about it. I get the observation here, right? And then I nudge the particles. I wait for 12 more hours. So I don't want to go from here and wait for the observation to come to assimilate it. I'll just wait for the observation at this particular point and then start to nudge the particles towards the prior here.
So it's like if you are starting your prediction,
After my,
delta tau, if tau is observational interval before the observation. So you are right.
no, I wait for the next observation. So I have my posterior here, all right? So now I'll wait for the 12 hours, I get the data. And then,
When you say you wait, so you run your particles one by one using the kernel, not using the model.
yeah, but I don't want to run the model without the next observation. I'll wait for the observation and then I run the model. That's the whole point. So I don't want to run my model and wait for the observation to come because then I can't use that observation. So I just wait here, next observation comes. So then,
The time of the model is observations in the future.
correct. I use observation. I don't know, because there's nothing about adaptive. I'm just observing them. Then I am pushing my system through. So I'm basically,
Conditioned on the
there's no condition. I'm just saying, instead of arbitrarily pushing forward my thing, I know the observation, I control the particles so that they are closer to observation.
So it is done by nudging, so you have time.
Nudging, exactly. Yeah, that's the nudging part. But I do the nudging part by an optimal control argument. And that's the beauty of this. Therefore, I have a neat way of doing it. But I do a neat way of doing it, but then I can't solve those equations. Then I said, hey, I throw my hand up and said, let's linearize it, get some control based on the linear part of it. I apply it. And it works very well. Yeah, I'll show you something. Yeah.
So in the homogenization, you can get the first order correction as well.
Yes.
And so you can improve this systematically in some sense.
I can, but so the amount of work we did to get those estimates was so much, that is, you can estimate them, but going to the next step is then for that to go, I have to go to the next further ones to show they are finite, all right?
No, but not in theory. Let's say,
Oh.
So let's say, okay, so you do the limit, so you get a homogenized system. That's a zero order.
Okay.
But then you
That's
get
what you
first
have.
order approximation, right?
Yep.
So in principle, if you could solve the PDE, that would give you a better approximation. You could have just a 0 plus epsilon times the first order would give you a better approximation.
Sure.
But would there be a particle filter associated with this? Does this have an interpretation in terms of?
Oh, I never thought about it.
I mean,
No, I never thought about what is the correction term, how to use it in my part.
Yeah.
No, I never thought about it. So I know.
I mean, the other question that's related, which might give. The question is, does the correction have a
Correction have a filter. This is what he's asking. Does the correction have a filter? Yeah. What is the interpretation of the correction in the filter, particle filter?
I mean, one thought that I have, but I'm not exactly in your setting, but last time you showed that if you are in the setting where the homogenized system is deterministic, noiseless, then you can get, already at the level of the system, you get a sort of central limit theory.
Correct.
If you subtract the noiseless system and you take multiply the square root epsilon, whatever
Yeah,
epsilon,
yeah.
you get a weaker version.
Weaker word. Sure,
And
sure.
then one question would be whether the first order correction would actually be the filter associated to the system you get from
Yeah.
the diffusive limit or something,
So that's right. So the question, if you go back to my results in Haspinski's classical case. So we had a deterministic equation as the average equation. But then we also, in Haspinski, also found the difference between, that's the correction, difference between the deterministic and the actual process converges to a Markov process, and he defined that Markov process. But what Ramon was asking me, actually, can we do the same thing here to see what are the implications of that in the particle filter? That's a very good question. I never thought about it. So I think now I'll think about it. Thank you. Yeah, so that's a good question to ask. Yeah, I think I'm, okay. You should thank me for leaving on time because I'm sure all of you are tired.